Some of the smartest aerospace engineers on the planet looked at this jet and flat out said, "No chance this ever flies." When Otto revealed the Phantom 3500, industry veterans laughed it off, calling it risky, unrealistic, and borderline impossible to certify. And this is where the disbelief really started. The first time engineers and insiders saw Otto's early aircraft, their reaction wasn't one of curiosity. It was one of confusion. There were no windows. None. Just a smooth, sealed fuselage, like something pulled out of a sci-fi movie. For people who've spent decades designing jets with oval windows cut into aluminum tubes, that alone felt wrong. Then came the pusher prop heritage. Early Otto concepts were tied to a rear-mounted propeller and even diesel roots. In business aviation circles, that's basically heresy. Diesel? Pusher? That's not luxury aviation. That's experimental, maybe military, maybe cargo, but definitely not a jet for high-end customers. And the shape didn't help. No visible antennas, no canoes, no steps, no fasteners. Just this eerily smooth, bullet-like fuselage. Engineers kept whispering the same thing. This looks like a black project. More DoD skunk works than something you'd park next to a Gulfstream on the ramp. Here's the uncomfortable truth. Appearance matters in aerospace. Engineers are trained to trust what looks familiar. Swept wings, windows, visible seams, proven layouts. When something breaks all of those visual rules at once, alarms go off. The logic was simple. If it doesn't resemble decades of successful aircraft, it must be hiding a fatal flaw. That instinct alone caused many experts to dismiss the Phantom 3500 before running a single number. And this is where the skepticism turned into outright disbelief. Wait, you're watching right now but not subscribed to the channel. Go ahead and smash that subscribe button so we can move on with the video. You did? Okay, cool. Now back to the planes. Otto wasn't just claiming a small efficiency bump. They were saying a 30% drag reduction could translate into nearly 50% lower fuel burn once the whole aircraft was redesigned around it. To most aerospace engineers, that sounded like fantasy math. Here's why. In aviation, gains are slow, painful, and incremental. A 1 or 2% improvement can take years and millions of dollars. Engineers are trained to be suspicious of anything that sounds too clean. You don't jump decades in efficiency overnight. The last time something this dramatic happened, you have to go all the way back to the Boeing 707 and later the invention of the high-bypass turbofan in the 1970s. That was a 35 to 40% leap, and it reshaped aviation. Since then, marginal gains, winglets, better materials, smarter software, nothing revolutionary. So when Otto's team talked about numbers that rivaled the biggest breakthroughs in jet history, the response was blunt. That kind of jump doesn't exist anymore. Engineers also saw an economic problem. Lower drag changes everything: engine size, fuel tank volume, structural weight. And redesigning all of that at once multiplies risk. Miss the drag prediction by even a little, and suddenly your engines are underpowered, your range collapses, and the airplane fails its mission. From the outside, Otto's claim looked like it violated the unspoken rule of aerospace. Progress happens in inches, not miles, and anyone claiming otherwise was assumed to just when it couldn't sound more unrealistic, Otto doubled down on laminar flow. To veteran engineers, that phrase alone carried baggage. Laminar flow had already been tested decades ago, and the verdict, at least in their minds, was settled. It was fragile, unreliable, a lab-only curiosity. Back in the 1970s, multiple programs tried to make laminar flow work on real aircraft. The theory was beautiful. The reality was ugly. Bugs on the wing, tiny surface waves in aluminum, panel gaps, fasteners, one small blemish, and the flow instantly turned turbulent. Drag went right back up. Those aircraft also flew lower, around 30,000 feet, where air density and Reynolds numbers are far less forgiving. Under those conditions, laminar flow couldn't survive the real world. So engineers moved on. Over time, laminar flow earned a reputation as something professors talked about, not something airlines could trust. Great for wind tunnels, useless for daily operations. Maintenance crews weren't going to polish wings to perfection after every flight. Weather, dirt, and wear made it impractical. So when Otto said laminar flow wasn't just part of the design, but the foundation of the entire aircraft, many experts didn't even bother arguing. In their minds, the debate was already over. They weren't being close-minded. They were relying on history. From their perspective, Otto wasn't introducing a new idea. They were reviving an old one that had already failed. And in aerospace, resurrecting a solved problem is often seen as the fastest way to crash a program before it ever leaves the ground. That assumption alone caused countless engineers to quietly write the Phantom 3500 off as another ambitious concept that would never survive reality.
The wing has about 90% coverage, and the fuselage has laminar flow up to the main cabin door. You see the Williams FJ44-4 engines, and they are a very reliable commercial off-the-shelf engine that have about 13 million flight hours on it. Great quiet power mode to run our accessories on the ground.
And then came the computational nightmare. Engineers quickly realized that standard CFD tools, computational fluid dynamics software, simply can't predict laminar flow accurately. These programs were built around turbulence assumptions because that's what most aircraft experience. Laminar flow behaves differently at a micro level, and even the slightest miscalculation can snowball into catastrophic drag misestimates. Imagine designing an entire jet around predicted performance, and your numbers are off by 5%. That could mean the engines are undersized, fuel tanks too small, or the aircraft can't even hit its range targets. For veteran teams, that was a red flag the size of a hangar. They knew firsthand that misjudging drag has destroyed more aircraft programs than almost anything else. That's why early reactions were so skeptical. Without a reliable model, the idea of building a commercial jet on laminar flow seemed reckless. And it wasn't a minor tweak. The whole airplane depended on it. Otto couldn't rely on existing software, so they built their own CFD system from scratch, running simulations on massive supercomputers with tens of millions of elements. This allowed them to predict drag at the micro level and iterate designs in ways conventional tools never could. For the engineers watching from the sidelines, it was audacious. Most said, "You can't even model this. If you can't simulate it, you can't fly it." Even if you could design laminar flow on a computer, most engineers assumed you couldn't physically build it. Aluminum aircraft construction is messy. Fasteners, panel gaps, steps, tiny waviness. Every millimeter is enough to trigger a transition from laminar to turbulent flow. For decades, that limitation made laminar wings mostly theoretical. No OEM dared dream of producing a full commercial jet with the level of smoothness required. Early skeptics immediately said, "Even if this works on paper, you can't build it." that was the consensus in boardrooms and engineering offices. Years of hands-on experience told them it was impossible. But Otto had a secret weapon: stealth manufacturing techniques. Methods originally developed for radar-evading surfaces allowed them to create ultra-smooth, uninterrupted skin panels. What was once a showpiece of defense tech became a production enabler for laminar flow. Most traditional manufacturers weren't prepared to adopt these techniques. They were too specialized, too expensive, or simply untested on a commercial scale. For Otto, mastering this was a breakthrough in itself. Suddenly, a concept long considered impossible was suddenly manufacturable. And that's exactly why industry insiders dismissed the Phantom 3500 at first. It wasn't just risky, it seemed physically, mathematically, and economically impossible. Until the engineering team proved otherwise. Just when it seemed like Otto was breaking every rule, there was another twist: altitude. Most jets operate around 40,000 feet. That's the sweet spot for standard designs, but it comes with a hidden cost: jet stream penalties. Flying westbound into 50 to 75 knot headwinds isn't just annoying. It can burn hundreds of extra gallons of fuel on long flights. Engineers had simply assumed that laminar flow would face the same challenges as normal jets, and most never even considered testing it at 51,000 feet, where the Phantom 3500 actually cruises. That extra 11,000 feet changes everything. The Reynolds number, basically a measure of airflow behavior, plummets. The air gets thinner. Friction drops. The very factors that destroyed laminar flow at 30,000 to 40,000 feet suddenly vanish. That old bug splat kills laminar flow myth? Busted. At high altitudes, a small insect on the wing doesn't disrupt the smooth flow anymore. Otto ran rigorous wind tunnel tests simulating 51,000 feet conditions, adjusting pressures to match the thin air. The results shocked skeptics. Laminar flow held perfectly, even with surface imperfections that would have destroyed it at lower altitudes. The long-standing assumption that laminar flow was fragile outside the lab collapsed in one stroke. For engineers steeped in decades of aerospace dogma, this was mind-blowing. The rules they thought were ironclad? Suddenly optional. Physics itself was on Otto's side. This is why early predictions of failure completely missed the mark. The Phantom 3500 wasn't just another jet. It was an entirely new altitude paradigm. And then came the next skeptic complaint. It's too small. Nobody will care. Large aircraft programs cost tens of billions to develop. Boeing's 787? Nearly $30 billion. Even the smaller C-Series ran $7 billion. Most engineers assumed Otto needed to start big to make an impact. Why waste time with a mini-jet? But starting with a 19,000-pound Part 23 aircraft wasn't a limitation. It was pure strategy. Part 23 certification reduces risk and shortens timelines, letting Otto prove the technology without bleeding cash. Every aerodynamic breakthrough, every laminar wing test, every CFD iteration could be validated in a manageable, low-risk platform. And don't be fooled. Small doesn't mean weak. The Phantom 3500 is faster, more efficient, and cheaper to operate than many super-mid jets, hitting the segment where profitability is highest. For Otto, it was about maximizing impact with minimal risk, turning skeptics' too small argument on its head. By the time anyone tried to dismiss it, Otto had strategically carved out a niche in the market, a smaller aircraft performing like a super-mid jet at half the cost. What looked like a weakness was actually a masterstroke, setting the stage for a technology shakeup that even the doubters couldn't ignore.
So this is a super mid-class airplane. similar to a Challenger 300 or Praetor 600 or a Cessna Longitude. The aircraft is the first transonic laminar flow aircraft.
And here's where the doubters really dug in: safety and speed. Early Otto designs raised eyebrows immediately. A single engine layout with radical laminar wings? In the minds of traditionalists, that was a recipe for disaster. In business aviation, customers insist on twin engines for peace of mind. One engine out over the Rockies or the Atlantic. No, thank you. Then there's speed. Time is money in private aviation.
300 aircraft order, over $5 billion order. That's one of the largest in history, if not the largest, for a single aircraft from a single fleet operator.
Flying slowly, even if efficient, isn't acceptable for high-end operators who demand performance and schedule reliability. Skeptics assumed that hitting twin-engine safety while maintaining radical efficiency would require compromise: heavier wings, smaller fuel tanks, or slower cruise speeds. Otto flipped that script. By combining lightweight construction, laminar flow wings, and high-thrust engines, they preserved efficiency without sacrificing safety or speed. The jet could meet customer expectations for redundancy and still cut fuel burn dramatically. For engineers watching, it seemed impossible. Conventional wisdom said trade-offs were unavoidable. But Otto proved you could tick every box at once: safe, fast, efficient. That's why skeptics struggled. The Phantom 3500 challenged not just aerodynamics, but the assumptions of customer psychology and market needs, all in one aircraft. And just when you thought it couldn't get riskier, regulators stepped into the picture. Radical aerodynamics scare the FAA. Engineers and certification specialists are trained to err on the side of precedent. Anything that strays too far from traditional design prompts countless questions, long delays, and sometimes program death. When the Phantom 3500 emerged, insiders whispered, "The FAA will never approve this." Otto tackled this head-on. Instead of reinventing the regulatory wheel, they built on proven components. Certified engines, avionics, and fuel systems were all part of the design. Only the aerodynamics and structure were radical, and those could be isolated for testing. That meant the FAA's focus was narrowed, reducing risk and speeding approval. In reality, certification is mostly about aero and structural integrity, not the exotic CFD predictions or laminar flow wizardry. Once the Phantom 3500 passed rigorous testing, all other systems, already certified, fell into place. Engineers assumed certification would kill the program because they couldn't imagine regulators accepting anything that challenged decades of norms. Otto showed that with careful planning, strategic testing, and incremental risk management, certification wasn't a barrier. It was just another design parameter. Suddenly, what seemed impossible on paper became achievable, and skeptics had to start reconsidering the entire program. And now we hit the production question, the one that made every skeptic scoff. Building 200 jets a year? That's a rate most traditional business jet manufacturers dream about, let alone a radical startup with unproven tech. Supply chains were skeptical. Component vendors, used to low-volume boutique production, were shocked at the scale Otto envisioned. Panels, avionics, engines, everything would need to flow in unprecedented volumes. Even suppliers who had seen high-tech military programs paused. They weren't prepared for a civilian jet demanding stealth-level smoothness on hundreds of units. Otto realized early that controlling tooling and production processes directly was essential. Outsourcing too much would introduce variations that could destroy laminar flow, wreck performance, or delay certification. For outsiders, this seemed like a massive gamble. Skeptics assumed production volume would collapse under complexity, and 200 jets per year was a fantasy. Then came a market-level validation. Flexjet's massive order. 300 firm jets, 300 options, billions in backlog. Suddenly, what looked impossible became profitable, tangible, and urgent. Production wasn't just feasible, it was demanded. For many onlookers, that was the first time doubt began to waver. And just like that, the narrative shifted. Flexjet didn't just place an order, they went all in. 300 firm orders, another 300 options. That's a $5 to $10 billion backlog in one swoop. Institutional investors started paying attention, capital flowed in, and suddenly skeptics who had dismissed Otto as a hobby project had to reconsider. At this point, the question wasn't if the Phantom 3500 would fly. It was when. First flight became inevitable. All the modeling, all the tooling, all the certification prep. They weren't academic exercises anymore. There were deadlines. The silence from critics was deafening. Engineers who had scoffed at laminar flow, mocked the shape, and dismissed production capabilities were now quietly watching every press release, every test video. The audacity of the program, once deemed impossible, had been validated by demand, capital, and strategy. It's rare in aerospace that a startup flips the script so completely, but Otto did it. The Phantom 3500 wasn't just surviving skepticism, it was rewriting what possible meant in private aviation. And let's be fair, those engineers weren't crazy to doubt Otto. Skepticism made perfect sense. Aerospace culture resists radical change. Decades of precedent, safety standards, and incremental innovation teach one lesson: leap too far, and you fail spectacularly. Otto wasn't asking engineers to make small adjustments. It required multiple breakthroughs at once. Laminar flow wings, extreme smoothness in manufacturing, custom CFD modeling, high-altitude flight optimization. Combine all of that, and the margin for error disappears. Most teams wouldn't even attempt it. Timing was critical too. Computing power and simulation techniques had only recently reached the level necessary to make Otto's vision plausible. Manufacturing technologies borrowed from defense projects allowed smoothness impossible in commercial production until now. Even altitude played a role. Physics itself helped solve what engineers assumed was a showstopper. In other words, doubt was rational. The risk was enormous. And yet, Otto orchestrated every breakthrough at the same time, stacking innovation instead of relying on a single miracle. That's why the Phantom 3500 shouldn't feel arrogant. It's a careful, calculated triumph, not a fluke. It challenges dogma while respecting the wisdom of those who assumed it couldn't be done. Industries that cling too tightly to precedent risk missing the next breakthrough. The Phantom 3500 proves progress doesn't wait for consensus. Today's impossible ideas might be tomorrow's reality. So, what's your take? Drop it in the comments. And if you enjoyed this, hit like and subscribe. More jaw-dropping stories are coming.